So I thought we'd start out with a little, another example of what we're going to see a lot in this unit, which is basically that as long as we recognize where there are efficiencies to be gained, or where there are places that we can do things to increase our precision, the solution is often going to be a fairly simple one in terms of what we actually have to do. Okay, so the idea is, suppose I need to do this calculation. I need to compute the trace of the product of two matrices. So if I do this naively, how many calculations am I going to carry out if I do this? So how many calculations do I have to carry out if I have to do A times B? Okay, so it's n cubed. So for every, I need to do 3 for loops basically to loop through taking each column, multiplying by a row. That's n operations. For each column, I have to do that n times. So that's now n squared, and then I'm doing n different columns. So that's n. Okay, so if we look at this and we carry this out as a sort of mathematical operation, this is n cubed. Then I'm going to do the trace, so I'm going to have to add up n numbers on the diagonal because that's sort of minuscule relative to the n cubed. So this is an n cubed order of calculation. Okay, but let's think about this in a little bit more sophisticated fashion. How many calculations do I really have to do here? Okay, so why is it n squared? Jimmy? Okay, so I only need to know the diagonal when I'm doing the trace. Everything on the off diagonals gets thrown away, so there's no point in ever having computed those values. Right? So if I go ahead and do the A times B, I'm wasting essentially all of my calculations, almost all of my calculations. Okay, so what I really need to do here is I've got some matrix A, I've got some matrix B, I'm computing the matrix, and I'm just interested in the diagonal, right? So what's the first diagonal element? Well, that's just the first column times the first row. Second diagonal element is the second column times the second row. And so on and so forth, right? So how many calculations is that? That's n squared, because this is n calculations, n multiplications. And then I do another one, that's another n, so I'm going to do n of these n different times, so that's n squared. Okay, so we should be able to do this calculation in essentially n squared calculations, not n cubed calculations. And if we don't, if we actually do this in its sort of, do it in a naive way, then we're wasting a lot of calculations. And if it's a large enough matrix, it's going to be a non-negligible amount of time. And if it's a really, really big matrix, it's the difference between it being able to do this calculation and waiting essentially infinitely long for the computer because it's going to go out of memory, and et cetera, et cetera. Okay, so how could I do this in R? So if I did this directly in R, I would do A times B, and I'd say, okay, and then I'm going to do something like the sum of the diagonal elements of this. So that's directly translating the trace of A times B into what it would look like if I coded it in R. Anybody see a quick way to do this in R? That's actually just a one-liner if I want to do it in the n squared context instead of the n cubed context. Okay, say it again.
Transpose B and multiply by.
Okay, so if I transpose B, what am I trying to do there in terms of how I wrote it out with the lines and the squiggly lines? Well, really, I'm just trying to multiply each element here. Well, as long as I transpose one of them, then I can then just do a direct multiplication in R, and then I can just sum up the results. So I should be able to do that as A times transpose of B. So that's going to give me a new matrix that has all of the elements times each other, and then I just need to sum over all those elements. So I should be able to do that as that. Okay, questions or comments? Okay, so again, the major work here was essentially in recognizing that there's no need to do this in this form, that we can rewrite the expression in another form. And once we recognize that we can do this in a more efficient way. It's not, it's a relatively simple thing to do. It's obviously simple to make this change, but even to recognize what we need to do is a relatively straightforward once we realize what the issue is. Okay, so so that was sort of in this one of the sections that I'd asked you guys to look over in advance of class. So I'm going to basically start with 1.9 here and talk a little bit about basis vectors and linearly independent vectors. So okay, so basically the idea of linearly independent vectors, which you guys should have run across before, is that I can't express any of the vectors as a linear combination of some set of the other vectors. And if I cannot do that, then I have a set of linearly independent vectors. They don't need to be orthogonal. It's just we can't express one as a combination of the others. So when I think about the rank of a matrix, and I'm going to think about this mainly in terms of columns, because oftentimes we're going to be thinking about a design matrix, a covariate matrix for regression. In that case, we're thinking about columns of the X matrix. Then the rank is at most the minimum of either the number of rows or number of columns. So when I'm thinking about regression, I'm basically going to be thinking about linear combinations of the columns of some matrix that we'll often call X. And I'm going to be taking linear combinations of those, and that's going to be my model for representing the observations in a reduced dimension. Okay, so we can basically, one way to think about what we're doing here is we're basically spanning a space with the columns of the design matrix. So in a simpler context, we could think about what happens when we just are in 2 dimensions and we have some vector x. Well, I can represent that as a linear combination of basis vectors, where I just choose basis vectors that are just oriented to the axes. So I can represent this x as a combination of this vector and then adding it with that vector. Okay, so I just need to scale this vector, add it with a scale of this vector, and I can get any vector x in this space. So these 2 basis vectors are basically spanning this 2-dimensional space. I can get any vector x as a linear combination of, actually, I guess I could have written it in different ways here. So if I write these as vectors that are both of unit length, then these are going to have to be the same length, and so I just need to scale this and then add it to a scale of that to get to x. So with these 2 vectors, I can basically span the plane. I can create any vector x as a linear combination of these basis vectors. But there's nothing magical about these 2, about orienting them in this direction. I could have rotated these guys, and I could equivalently span this 2-dimensional space with, say, this set of orthogonal unit 1 vectors. So those could also be the basis vectors for the space. But I could also have done that with vectors that are not orthogonal to each other. So I could have, as long as I don't have my second vector just be a linear scaling of the first vector, I could also span this space with some other vector here, as long as it's not linearly dependent on the first of the vectors. Okay. So that's thinking about this just in this 2-dimensional context. Okay, so questions at this point? Okay, so now we can think about what happens if we want to think about this in a regression context. So now in a regression context, we can think about having, let's say, p of these different columns. So here we have p columns, we'll have n observations. And then let's suppose that I have q, out of these p, I have q linearly independent column vectors. So that means I can, with these vectors, I can span a space of dimension 2, just like here I was spanning a space of dimension, spanning a space of dimension q, just like here I was spanning a space of dimension 2. And we can think of these guys as basically as basis vectors. And the same idea as I was saying here is they don't have to be orthogonal to each other. Although in say ANOVA context they might be orthogonal to each other. But I can still span this Q-dimensional space. And what happens when I compute X transpose X is I get a P by P matrix, and as long as I'm going to get Q non-zero eigenvalues. So depending on how many sort of redundant columns I have, that's going to correspond to eigenvectors of this matrix that have that are zero. So in many contexts, we're going to have P of these linear independent vectors. X transpose X is going to have P non-zero eigenvalues. It's going to be invertible, et cetera, et cetera. Okay. Let's see, what else did I want to say here? Okay, and then, sort of as you guys have seen in, much of this should review, sort of as you guys have seen in a regression class, I can think about how does the size of n compare to the size of q, and what does that mean for fitting a regression? Well, in the context in which I can draw it, let's suppose that I have a two-dimensional space, and if I just have one observation, so here I'm going to have q equals 2. If I just have one observation, I'm under constrained. I can basically have an arbitrary number of basically fits of this regression. And if I have two observations, so this was n equals 1, now if I have n equals 2, I have a unique solution here. And as soon as I get n bigger than q, then I can't exactly fit the observations anymore, but I can find the regression line that minimizes some criteria, and then I can go ahead and compute that regression. So, I think it's still useful to see this and think about this. Obviously, in most cases, we're dealing with more than two regressors, and so we're having to think in a higher dimensional space, but I still sort of come back to this sort of image when I try and make sense of what's going on when I've got q equals 3 or q equals 4, or much larger values for q and much larger values for the observations. Okay, questions or comments? Okay. Oh, there's a typo here. This should be n bigger than q and not n bigger than p. Okay, so another way to think about this, and you guys may have seen this also in a linear regression class, is to think about what we're doing when we fit a regression, which is basically projecting onto a lower dimensional space. So I guess sort of the easiest way we can do this is in 3 dimensions. So if I'm thinking about a 3-dimensional space with the axes being along the wall here, and I think about my observation vector, say I have n equals 3, and I have some observation vector that's sitting out here in this 3-dimensional space. And now I can think about what's represented by the columns of my X matrix. Well, if they were orthogonal, then I could think about them as being the lines here that define the room. And what am I doing when I fit a regression? I'm taking the observation vector and projecting it down onto the floor. Well, in other more complicated contexts, I'm not going to have those nice orthogonal basis vectors, but I'm going to have, based on the columns of the X matrix, I'm going to be defining two vectors, say, coming out of the corner here. And maybe those two vectors come out to here, and I can think about linear combinations of these two vectors as spanning some plane. Okay, so that defines a 2-dimensional subspace. And now I have my 3-dimensional observation vector, I'm projecting that down onto that 2-dimensional plane. So it's the same story, it's just a little bit more complicated in sort of thinking about it geometrically. But that's basically what's happening when we're fitting a regression. Okay, so we're going to be mainly thinking about what are the characteristics of columns of a matrix, because oftentimes we're going to be thinking about a regression type context, and then it makes sense to be thinking about the columns because we're often thinking about linear combinations of those columns. And because we're working with the X transpose X matrix. Okay, so let's talk a little bit about characteristics of various matrices in terms of eigenvalues and eigenvectors. And again, we're going to be thinking about sort of linear combinations of vectors when we do that. Okay, so the idea is that basically square matrices you can decompose as an Eigen Decomposition. Any matrix, square matrix A can be decomposed as gamma, lambda, gamma inverse. So the columns of gamma are the eigenvectors, and lambda is a diagonal matrix, and those are the values on the diagonal are what we call the eigenvalues. Okay, so in this case, the number of non-zero eigenvalues is the same as the rank of the matrix. So usually we're going to be working with square matrices, and actually usually we're even beyond that, we're going to be working with symmetric matrices. So things get simpler in that case. Okay, so so if the matrix is symmetric, then it turns out the eigenvectors and the eigenvalues are real, which doesn't necessarily have to be the case in this other context. And gamma is actually an orthogonal matrix. So in that case, gamma inverse is going to be the same as gamma transpose, and this is the Eigen Decomposition that we're usually thinking about in a statistical context. So we can decompose it as basically as a matrix of columns, which are the eigenvectors, and then weights, which are the eigenvalues, which are the values on the diagonal of this lambda matrix. Okay, so we're going to focus on symmetric matrices, and in that context, we're going to have a bunch of equivalences that we can write out. And so if we have A being a positive definite matrix, then that's equivalent to saying that A is just a covariance matrix, and we'll talk about that in a minute. And that's equivalent to that for any vector x, x transpose AX is bigger than 0. That's also equivalent to all of the lambda i's. So I'm going to denote lambda as being the matrix lambda 1, lambda 2, up through lambda n, this diagonal matrix. So all of these eigenvalues are bigger than 0. That then implies, although that's not an equivalence, that the determinant of A is bigger than 0. This is equivalent to A being invertible, and that's then equivalent to A being non-singular. So when we're dealing with linear algebra, we often end up, there are a lot of these different terms that are getting thrown around, and I just wanted to sort of throw them all up here so we can sort of see the relationships between them. We can also have A being a positive semi-definite matrix. And that's essentially equivalent to a constrained covariance matrix, and we'll talk about what we mean by constrained in a little bit. And now we have x transpose AX bigger than or equal to 0 with at least one, with the possibility of with at least some x's giving us 0 in this context. Okay, and then we have lambda I bigger than or equal to 0. This then implies that I have the determinant of A equal to 0, and that A is not invertible. And A is singular. Okay, so let's see, what do I want to say about these various bits here? Okay, first let's think about this part here. So if I have that the covariance of some y, vector y, is equal to the matrix A, then I can take x transpose y, say for one of these x's, And I can think about what's the covariance of x transpose y. So that's just going to be x transpose times the covariance of y times x, which is just x transpose a x. So what's x transpose y? Well, that's just x1, y1 plus x2, y2 plus up through xn, yn. So what have we got here? We're just taking linear combinations of y's. Y's are the random variables, and I'm taking linear combinations of those. So this expression here is just the covariance of some linear combination of the y's. And what this says is if I have a covariance matrix, well, okay, what does that mean? It means that any linear combination of the elements in my random vector have a positive variance. So that's one way of looking at this. And it tells us, okay, why am I saying that if I have a positive definite matrix that it's the same as a covariance matrix? Because I can think about these matrices in this kind of fashion. Okay, so if it is positive definite, then that also means that I have all non-zero positive eigenvalues and that I can invert the matrix. And if I want to do this decomposition in R, all I need to do is I need to take the matrix that I'm interested in decomposing and say eigen of A. So that's going to do this eigen decomposition. It's going to give me back a list. And in that list, I'm going to have the eigenvectors, which are going to be the vectors component of that. And those are going to be this matrix gamma. And I'm going to get a vector back, a vector as well as a component of this result, which is going to give me the eigenvalues. So I can do this decomposition easily, although for large matrices it takes a bit of time to do. So let's see here. Just want to see if I want to say anything else about this. Yeah, I think the other things I want to mention are going to come up as I talk through a few of these examples, talk about this eigen decomposition in a few specific cases in a second. Are there any questions before I do that? Okay, so what I want to do is look at this eigen decomposition in a way that in the form that we use to generate random variables, random vectors. And when I do that, we're going to see that there's a nice interpretation for what these lambdas represent and for what the columns of gamma, what the eigenvectors represent. Okay, so the idea is, let's think about generating random variables that have a covariance that is this matrix A, and how we would go about generating that. One way we could go about generating that. There are multiple ways. Okay, so one of the ways we could do this is we could say, okay, I want to generate y such that the covariance of y is equal to A. So one way I can do that is I can write gamma lambda to the 1/2 z, where z is standard normal. Okay, so z is just a collection of n independent standard normal random variables. So what am I doing here? Well, I'm just taking my eigenvector matrix. I'm taking the square root of my eigenvalue matrix, and all that corresponds to doing is just taking taking the square root of each of those diagonal elements of the matrix. So what does that do? Well, I can think of this. So I could generate y in this way. But if I think about doing it that way, another way that I can think about is combining these two components and just multiplying by this. So I could think about this also as y as being gamma times z star, where I have zi normal 0 lambda I independent. So if I think about this, what is this? Well, I can just sort of write this out graphically as I've got my columns which are the eigenvectors. And now I can write that out as z1 star up through zn star. So what am I doing here? I'm just taking linear combinations of these columns where the weights correspond to the z's. So I'm taking z1 star times the first column, z2 star times the second column, and so on and so forth. So I'm generating y as linear combinations of these eigenvectors. I can think of these as basis vectors. I can think of them as sort of patterns. I'm taking combinations of these different patterns. And the weights are going to be the z's, and the magnitudes of the weights are in accordance with the lambdas, which are the eigenvalues. Okay, so the scaling goes by is based on the eigenvalues, and then the patterns that I'm doing the scaling upon are the eigenvectors. So that's one way of sort of thinking generatively about what do these eigenvectors and eigenvalues mean. These are basically variances for weights. The weights determine how I weight the different patterns. All right, questions about that?
And should it be square root of lambda?
So the lambda is the variance, and then the standard deviation would be the square root of lambda. Yeah, so I could think about generating this as I could say, okay, zi star equals square root of lambda I times the original zi, where this was standard normal. Other questions? Okay. So that helps now in terms of, I sort of laid all this out about these positive semi-definite matrices, sorry, this line of things here, without saying too much about that. And part of the reason I did that was I wanted to sort of wait until we could sort of start thinking about that, having seen this over here. So if I have x transpose ax bigger than or equal to 0, then A is, you can say, it's either positive semi-definite or non-negative definite. And I've got an eigenvalue that's equal, at least one eigenvalue that's equal to 0. Okay, so let's think about this in that context I've got over there. So what does it mean when one or more of these eigenvalues is equal to 0 in terms of these patterns here? So in this generative context, I'm taking linear combinations of these eigenvectors. So if one of these guys happens to be 0, what does it mean? Well, when I combine these eigenvalues, one of these z stars is going to be 0. It has no variance. And so I'm basically excluding one of these columns from my combination. So I'm basically generating a random vector, but that random vector doesn't have as much freedom in terms of as many degrees of freedom in terms of flexibility of the randomness that I'm generating, because I'm not including any of one of these, any variation from one of these components of the eigenvectors, one of these eigenvectors. So and remember, these guys are orthogonal. So I'm working in a reduced dimension subspace. Instead of having a linear combination of n columns, I'm going to have a linear combination of less than n columns. So I'm going to be in this reduced space. So that's one way of thinking about this. Okay, so the second question I have here is, and this now gets to this idea of numerical precision and some of these things that we're going to see in the next couple days, is suppose that I have an eigenvalue that is very small. And instead of actually using it in some calculation, I just go ahead and set it equal to 0. Is that going to have a big impact on the resulting y's that I generate? Hopefully the answer is no. So if one of these eigenvectors is already small, then when I think about the variation in y, then whichever eigenvector corresponds to the eigenvalue that was near 0, well, that was adding a relatively small proportion of the variation when I generated the y to start with. So if I go ahead and set that eigenvalue to 0, let's suppose it's the last one, this eigenvector was not contributing much variation to the y's because it had a small eigenvalue, and therefore the zi star that corresponds to it is going to be small. If I go ahead and zero this out, I'm really not affecting the result very much because of the fact that this wasn't contributing much even when I had it non-zero, because of the fact that the zi star would be relatively small because it has a small variance. Okay. So the difference in terms of the resulting y is going to be relatively small. Mathematically, there's a difference in that I'm in this n-1 dimensional subspace if I set it exactly equal to 0, whereas if it's not quite equal to 0, I'm still in this n-dimensional space. But in terms of the sort of numerical difference between a y generated in one of these two ways, it's not going to be very large. Okay, so questions about that? Okay, and I can also think about what would happen if I start thinking about the inverse of A, which we call the precision matrix instead of the covariance matrix. So if I have an element of the precision matrix that is very large, it means I have high precision, which corresponds to having low variance. And vice versa, if I have one that's very small, I have low precision, which corresponds to high variance. So when I was sort of thinking through what would be a good way to think about this in terms of explaining it, I came up with the following. We'll see if this seems helpful. That I can think about generating y normal some mean vector mu and then this covariance matrix A that I've been talking about. So everything over there, I think I probably didn't say it, but was implicitly with having a 0 mean vector. But I can, of course, just generate y according to the recipe over there and then add to whatever y I get. I can just add the vector mu, and that's going to then generate a multivariate normal random variable that has mean mu and covariance A. But the thing I want to think about in this context is what happens when I've got, say, one of these values very large. So the precision is very large. So that means the variance is small. So I've got a lambda I that is small. So one way I could think about doing this is I can say this is mu plus the first column of gamma times z1 star on up through the nth column of gamma times zn star. And now if I think about having a high precision for one of these components, so the inverse of the diagonal element is large, one of these is small, let's suppose that it's the last one. So this is small, so then if I generate a z star, this is essentially going to be equal to 0. But what does it mean when I say I have high precision in this dimension, in the gamma n column dimension? Well, if I go back to thinking about what mu looks like, I could think about this vector mu that's in this n-dimensional space. And I could think about basically projecting mu onto the columns of the eigenvector matrix. So I can basically decompose the variation of mu into something times gamma dot 1 up through something times gamma dot n. And if I think about it that way and focus on this piece of it, then what's happening when I have high precision for one of my components? Well, all of the variation in that component is coming from the mean vector, which I know precisely. And none of it's coming from the random component that I add on to the mean vector. So that's one way I sort of think about what does it mean to have, when I'm thinking about these precision matrices, and what does it mean to have high precision? Well, it just means there's no random variation from the random piece of it. And if there is a component, then presumably this mu vector may well have a component variation in that direction, in the direction of this column. And that's going to be the only variation in that direction. There's nothing coming from the random piece. Okay, so any questions or comments? Okay, so then the next thing I want to talk about a little bit was generalized inverses. And this, again, relates to this idea of having having situations where I'm monkeying around with 0 values for the eigenvalues. And it deals with this idea that we have a constrained covariance matrix. Okay, suppose that A is not full rank. So I'm in this context here with all of these various relationships. Then I can't invert it. Okay, so I can't do A inverse. But I can come up with something called a generalized inverse. So that's defined as a matrix A minus that satisfies this property. And there's a particular generalized inverse called the pseudo inverse, which we usually denote, or some people often denote this as A plus. And the idea is that we can still do something like doing A inverse times B. So if we want to solve the system of equations AX times B, so for example, we could have X transpose X inverse X transpose Y, or we could be working with covariance matrices, and so in that case, we are often going to be wanting to find X such that, that this set of equations is satisfied. Well, if I can't invert A, then I can't do this set of calculations. But what I can do is I can find X equals A plus B, and that's going to be the solution of the system that has the shortest length for the vector X. So numerically, one way that we can compute this is we can take, we can do an Eigen Decomposition. If we do this Eigen Decomposition, we can think about what's going to happen relative to these relationships. So what's going to happen is I'm going to have one or more of these eigenvalues that's equal to 0. If I wanted to invert the matrix, so let's think about this for a moment. So if I wanted to invert A, and A was actually invertible, one way I can do it is I can just say, I can compute the Eigen Decomposition, and then do that. Just take the inverse of this diagonal matrix. That's easy. It's a diagonal matrix. I can just invert each of the elements. And if you multiply A times A inverse, you'll see that things cancel. These guys are orthogonal, so they're going to cancel. You're going to get back the identity matrix if you just work through this. Okay, but the problem is if I now have some of these elements being zeros, so my matrix is lambda 1 up through lambda n, I now try and go through my recipe here and invert elements here. If one of these is 0, all of a sudden I have a big problem. I try and do 1 over that, I'm going to get infinity, and I can no longer do my calculations. So the idea of the pseudo inverse is to take this 0, and now when I'm computing this, instead I'm going to compute gamma lambda plus gamma transpose. And what is this? Well, lambda plus is just going to be equal to 1 over lambda 1, 1 over lambda 2, and then whenever I have a 0, and I would be about to put in an infinity there, I'm actually going to replace it with a 0. So I'm going to keep the original 0 that was there. Okay. So in some ways this seems a bit awkward because I'm in fact replacing something that's very, very large, the infinity, with a 0. So it seems like I'm sort of doing exactly the opposite of what I should be doing in some sense. But what we're going to see is that this actually makes some sense in some particular context, or it sort of generally makes sense, but we'll see some particular context to try and help us see why that makes sense. Okay, so remember what was happening when we have eigenvalues that are equal to 0. We worked through that before in that generative context. If I have a 0 eigenvalue, I'm not including any component, I'm not including any variation from one of the components of variation, one of the eigenvectors. So if I do this pseudo inverse trick here, I'm basically taking that eigenvector, which corresponds to an eigenvalue that was 0. So let's see here. So we had an eigenvalue that was 0. So that is 0 variation. And wait, I'm managing to confuse myself here. Oh, right. Okay. So the reason why is I'm working now with the inverse of the matrix. So okay. So I'm trying to think about A inverse. And ideally what I would like to do is this, and that would correspond to having elements of, so that would correspond to having 1 over lambda I So these are the eigenvalues of A inverse being equal to infinity. So that would be the variance is equal to infinity. So if I were trying to generate, say, y with covariance of y equal to A inverse, the problem is I have infinite variance on some of these, on at least one of these eigenvectors. And what my pseudo inverse recipe says is turn that variance into a zero. So instead of it being infinity, make it into a zero and say I have no variation for that eigenvector. So I'm basically zeroing out that column, even though originally I said I had infinite variation for that column. Okay, so what does it mean if I do that? Well, let me give you an example and we'll see what happens. So there are models that are called autoregressive models. These come up in time series and when you're doing smoothing of various sorts. And a first order autoregressive model for y's for time 1 up through time capital T has that the expected value of y given all of the other y's, expected value of y at the ith time point given all of the other y's, its mean is just the average of the value of the previous time point and the value of the next time point. So that's a first order autoregressive model. You can sort of see that it would do some smoothing because I'm basically saying any value is basically going to be the average of the two neighbors. You can see there's sort of some smoothing that would be induced there. A second order autoregressive model has that the expected value of yi given all of the other y's is a different kind of averaging where I take 4 times the nearest neighbors and then I take -1 times the second nearest neighbors. So that does a little bit more smoothing because it's sort of spreading the smoothing out over more of the neighbors. So it turns out if you have these autoregressive models, you can actually figure out that the precision matrix for y for this first order model, this one here, looks like this. The guys on the diagonal, the number of neighbors, in this case 2, or the weights on the neighbors, which sum to 2 here. And the -1s say that these guys are neighbors, so this is basically, say this was the 3, element. Suppose this is the 2, element of the matrix. This says the first and the third time points of the neighbors, that's what the -1s correspond to, and so on and so forth. And in the second order model, we end up with a precision matrix that looks like this. So sort of where this comes from is not all that important, but the thing to see here is that if we so I'm going to make one of these precision matrices. Okay, so they look like this. If I do an Eigen decomposition of that, I can do that. I can look at the eigenvalues, and you'll notice that one of these eigenvalues is 0. So this precisely corresponds with this situation I'm talking about here of one of these positive semi-definite matrices. And I can look at the eigenvectors, and if I look at the 5th column, which corresponds to that 0 eigenvalue, what I see is that that 5th column has all of the same values in it up to the precision with which we can represent numbers. So this is basically a constant vector. It's just a scalar, 0.447, yada, 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 times the vector 1. So if we go back to that generative context of generating a vector y as a linear combination of eigenvectors, this component of variation is just a constant, basically. It's how much do I add, what constant do I add to when I'm generating the y's. So what does it mean when I do this pseudo inverse trick here? It says, okay, what this says is this is a model that has infinite variance on the constant vector. So I basically have no information about that constant vector. And what I'm going to do when I do the pseudo inverse is I'm going to set the variance of that equal to 0, and I'm going to include no variation for the constant vector. So I could, for example, come up with the pseudo inverse by taking those original eigenvalues, inverting them, except leaving out this 5th one that if I inverted it would go from being a 0 to being infinity. So if I do that, I can now generate y's according to this covariance, but with this pseudo inverse by taking the vectors and matrix multiplying, or matrix vector multiplying by the eigenvalues. It looks like I should have done a square root in here, so there's a typo in my code here. Times a random set of independent standard random normals. So this is the pseudo inverse recipe for generating y's in this case. And if I do that, I can see, okay, I get a set of y's that are generated according to this covariance matrix here, the A inverse. But if I look at what's the sum of the y's, that's 0. Okay, and it's 0 because I zeroed out the eigenvalue corresponding to the eigenvector that was the constant vector. So I'm including a 0 contribution from the constant vector in my generation of my y's. And as a result, any vector of y's that I generated by this recipe would have mean 0. They would sum to 0, they would have mean 0. So another way of looking at what I've done here, and that goes back to this here, is I've generated values that are that have a constraint in there. And the constraint in this case is that the sum of the y's is 0. There's no contribution from a constant in this set in this vector y, or in any other y's that I could generate in this way. So when I set the eigenvalue equal to 0, I'm basically inducing a constraint. I'm inducing a constraint into the problem, and I'm zeroing out one of the eigenvectors, and that amounts to inducing a constraint. And I basically have to do that in this case because I can't generate basically a mean that has infinite variance. So the only other thing that I can sort of basically do is generate under this constrained model and just recognize that I have no information about the mean. So that's what this. If I go back to the PDF, this model here, this first order autoregressive model, is basically a model that has no. We can think of it as a model that has infinite variance on the constant vector, so it essentially has no information about that constant vector. So the only way I can generate under that model is I can basically generate where I constrain the mean to be 0 and recognize that I have no information about the mean. And analogously, if we looked at this matrix, which corresponds to the second order autoregressive model, what I would see is that there are two eigenvalues that are 0, and they correspond to a constant vector and a vector that corresponds to linear variation. So here, the constraint that I would have to introduce would be I'd have to introduce two constraints. One of the constraints would be that the mean is 0, and the other constraint is that basically the linear term in the variation is also equal to 0. So there's no slope in the y's that I would generate. But they could have sort of second order and third order quadratic and cubic kinds of variation. Okay. Another way of thinking about this in this case is that basically I have a non-identifiability in the model. In the first case, the mean was non-identifiable. In the second case, the mean and the linear components were non-identifiable. And so again, the idea is I would constrain them because I basically can't deal with the non-identifiability. And then let me just close by saying one way I could think about writing out a statistical model that has this property that uses this smoothing model for the data would be I could write it as, say, with the first order model, I could write it as mu plus y. I could say y corresponds to that model, that smoothing model. I put that constraint in there that says the mean of the y's is going to be 0, and then I add in a term that's just an overall mean, mu. And that accounts for the variation in that direction. So we could think of this as being adding just a constant in, and then the variation in the y's does not include the variation variation that corresponds to just adding a constant to each element of the vector y. Okay, so let me close there, and next time we'll pick up with computational issues and numerical precision for linear algebra.